Hi, everyone. Are there people? Okay. Uh, so hello, everyone. Thank you so much for joining this webinar today. My name is Allie Yamagata from Saint-Gobain, North America, and I'm the YPN Cements Division Liaison. I'm gonna be the host for today's webinar. So before we start, I'm gonna share my screen here. I'm gonna share my screen. Okay, settings. Sorry. Okay. Okay, let me share my screen real quick. Second screen. No, screen one. Okay. Yeah. Before I'm starting, I'm going to quickly talk about ACerS and the benefits of being a member. And so being a member of ACerS can give you a lot of benefits. There's it gives you access to resources that allow you to continue to learn and grow, gain recognition with awards and scholarships, apply for support to travel and attend conferences. And There is also the President Council of Student Advisors. There are many ways to have leadership positions around ACerS in the different divisions. This is the ACerS membership path, depending on where you are in your career. If you're students, we have the Material Advantage student program. For graduate researchers, we have the Global Graduate Research Network. And then there is the SACEF membership. If you're a professional, have never been involved in ACerS, you can join us for free for a year, and the second year is only $20. After that, there's the individual membership, which is $120 per year. We have a really good mentorship programs as well, which is one of my favorite things. So this webinar is brought to you by the Cement Division, and it's one. So what is the Cements Division? It's one of the 11 divisions of the American Ceramic Society, and we advance the fundamental material science of cement with an emphasis on nano and microscale research, and develop new technologies for concrete. What's in here for you? You can connect with industry professional. We organize meetings, symposia, and related events to stay current. You have access to the member resource and industry publications. You have a bunch of leadership development opportunities, awards and recognition, and access to peer-reviewed journals from ACerS. We have this yearly Advancing Cement-Based Materials meeting. It's a science-based meeting focused on the world's most used construction material. It's a unique event for cement chemists. We have a research showcasing presentations and board session, and opportunity to network with professionals for academia, industry, and research labs. We also have the giving back to students, outreach, travel, sports, and leadership in community positions. So I would like to announce that the Cements ACerS meeting, the 50 Advancing Cements-Based Materials, is officially open for abstract submission. So if you want to check out one of the past conferences on cementitious material advancements, this is D1. And it's going to be in June 11 to June 13 in Colorado Boulder. We have some sponsorships opportunity this year. So if you're interested in a sponsor for this conference, we have different possibilities. It's a way to boost brand visibility, foster a positive reputation for your brand, and access target audience, have a public outreach and credibility and reputation by having your brand associated with ACerS. For more information, contact Vicki Evans and evans@ceramics.org. Yeah, submitted by March 15. Okay, so now I would like to introduce our speakers, which is also happens to be a good friend of mine. So Agnieszka Jędrzejewska is an associate professor in the Department of Structural Engineer at the Silesian University of Technology in Poland, and a structural engineer. Her research focuses on restraint-induced thermal shrinkage, cracking, and reinforced concrete structures. She integrates advanced advanced numerical modeling, large-scale experimental studies, on-site structural monitoring, and analytical model development for design and standardization. Throughout the presentation, you can actually send Q&A. We're gonna have a Q&A session after the talk, so feel free to send the questions as you have during this presentation, and we're gonna answer them after her presentations. There's actually like a box that you can find somewhere there in Zoom. And now I would like to give the floor for Agnieszka. Thank you.
Thank you. So, Alessandra, thank you for having me here today. Thank you for invitation. It's a great honor to have my work acknowledged. So I will start with sharing my presentation, if I may already. Okay. I hope you can see my presentation. If you can please confirm, Alessandra, that everything is okay for the viewers.
Yes, everything is perfect.
Okay, perfect. So once again, thank you everyone for joining us today. So as Alessandra said, my name is Agnieszka Jędrzejewska, and today I would like to present you a short lecture on hydration-induced cracking of reinforced concrete structure. And as the name say, I would like to present it from a European perspective, which might be some new knowledge for some or even most of you. But before I begin, I would like to tell you something about my background. So as also it has been said, I am currently an associate professor at the Department of Structural Engineering of the Silesian University of Technology in Gliwice in Poland. I currently hold a habilitation degree, which I gained last year following my long journey through bachelor, master, and PhD, all of which were within structural engineering. I am currently working at the Silesian University of Technology as associate professor, where I had to climb a long ladder of course, all the steps before. My research interests are focused mainly around reinforced concrete structures, but mostly from the structural engineering point of view, not that much from the material. But I especially am interested in massive concrete structures and restraint-induced cracking, hence this is the topic of my today's presentations. So the skills that I use within my research encompass such as structural design, modeling and simulation, but also analytical models which are used for standardization purposes. And I focus a lot on knowledge transfer between research, between academia and between the industry, so the practicing engineers. And in my work, I value a lot the collaboration that I gained, mostly through such initiatives as Cost Action and RILEM. And thanks to that, I can work now within a large network, both regarding research, but also companies. And I would like to present briefly a timeline of my research so that you know my background, my collaboration, and the milestones of my research work. So actually my research work began already in 2011 within a research project that I was conducting in Poland together with my future PhD supervisor, Professor Barbara Klemczak. And this is how I started my PhD, which was related mostly to numerical modeling of thermal and shrinkage stresses in externally restrained reinforced concrete structures. At the end of this time, I had the pleasure of visiting École Normale Supérieure de Cachan. So this is actually a place where I met with Alessandra, and under the supervision of Professor Farid Benboujema, I was continuing my work related to numerical modeling of massive concrete structures. In 2015, I have successfully defended my PhD thesis, and also the same year I joined a very interesting initiative, the Cost Action TU1404, which was related to service life design of massive concrete structures of or general the structures which are based on cement-based materials. And within this action, I was responsible for a work group which was related to modeling of massive concrete structures. At the same time, I also joined RILEM, and I actively participated in the first of many technical committees within RILEM. So the first one, 254, was related to thermal cracking of massive concrete structures. And among many outcomes of this technical committee, we have produced a state-of-the-art report, which is, I would say, currently one of the most up-to-date books about the problem of thermal cracking of massive concrete structures. Then I continued my work building my research network, and thanks to my work within cost action, I established a cooperation with a technical university, the Graz Technical University in Austria, with Professor Dirk Schlicke. And it was a long-lasting partnership within which we investigated the problem of macro cracking of externally restrained structures, and some of the outcomes I will present during this presentation. We have realized a couple of research projects together, which were also connected with me visiting TU Graz on multiple occasions. I have also continued my work within RILEM. I am currently a member of another technical committee, which is related to early age and long-term cracking of reinforced concrete structure. And we are also producing a lot of nice research outcome, also thanks to a very strong cooperation with engineers from ARU. Hopefully by the end of this year, we will publish another interesting book about cracking of concrete structures. This will be generally on the topic of cracking, but also with a special focus on cracking, which is caused due to the restraint of imposed deformations. In the meantime, I gained my habilitation degree, which happened at the end of last year. And I am also continuing my research on the topic of cracking of reinforced concrete structures. And as I believe many of people nowadays, I am investigating the possibilities of using artificial intelligence and machine learning. That's why I have recently joined another RILEM Technical Committee on a data-driven concrete science. I am also currently realizing an interesting research project, which is related to the application of ontologies, so knowledge-driven approaches to concrete design in cooperation with the University of Minho in Portugal, which is also related to multiple visits. So currently I am actually not in Poland, but I am in Portugal realizing this project. So regarding today's lecture, the outline of the lecture would be as follows. I will start with explaining the problem, the phenomenon of restraint-induced cracking as a general, and then I will focus on the cracking which happens in externally restrained elements such as walls, which is of my main focus research-wise. Then I will move to the design methods that are being used around the world, with a special focus on the European approach, but also in comparison to the approach that is used in United States. I will make some comments about the, let's say, disadvantages of these methods or limitations of these methods, and then I will move forward with some recommendations of how to better handle the design process to obtain more accurate results. And then I will finish this lecture with some key takeaway conclusions. So let me begin with what I promised you at the very beginning. So let me start with explaining the problem of the restraint-induced cracking. So when we talk about cracking, or when engineers talk about cracking, we usually think about cracking that happens in hardened concrete during service life of a structure, when cracks are caused by the service loads that are predicted during the design. So of course we expect this cracking, and even at the design stage we predict that they will happen, and our focus is on limiting the width of the crack. However, what most of the engineers don't realize or neglect is that cracks can appear actually much earlier during the life of the structure. So one of the most very important problems related to cracking are cracks which occur during the hardening phase in concrete, so between setting and maturity, as well as the cracks that can happen already in fresh concrete during setting. So as long as this first type, like cracks in fresh concrete, usually do not have that much of structural meaning, the cracks which happen during hardening are already very dangerous, because if they appear, and they usually do, it means that when the structure is put into operation, it is not in a zero stress state as it is usually assumed, but it is already in a way pre-stressed and pre-damaged. And what is the reason of this crack? So where the problem lies? So it lies inherently in the nature of concrete, because as we all know, concrete is a composite material that is produced from a mixture of water, aggregate, and cement. So when we produce concrete, we want to produce an artificial stone in which the components of the aggregate are submerged in a cement matrix, which is produced due to hydration of cement with water. So on one hand, this is the way how we obtain this artificial stone. So because of this hydration of cement and water and production of this cement matrix, we are obtaining a desirable stiffness and strength. So what is actually our goal? But at the same time, we usually forget that this process has some negative effects. So due to the hydration, there are some phenomena that happen in concrete, which are related to temperature and shrinkage. So first of all, we must remember that cement hydration is a highly exothermic process, which means that during this process, large amounts of heat are produced, which lead to increase of the temperature in the element. Moreover, we need to remember that hydration of cement, so bonding of cement with water, causes the so-called autogeneous shrinkage, which means that the volume of the product, the cement matrix, is a little bit smaller than the total amount of water and cement. This is another reason why we have decrease in volume. Finally, some of the water which we add because of the workability requirements is not needed for the hydration, and this water is being removed due to drying shrinkage. So these three processes cause volume changes, and the problem becomes even more complex because the importance of this phenomena depends on the so-called massivity of the element. So I think that each of us, if we hear a name massivity, can pretty naturally understand what massivity is. So we usually understand it as a large volume of something. So we can imagine that as the massivity of the element increases, the influence of thermal strains, which are connected with the production of the heat, also increases. The same goes with the autogeneous shrinkage, because even though this process is related to mostly to the type and amount of cement, it is also a temperature related or temperature dependent process. So if the massivity increases and the amount of heat increases, then also the effect of autogeneous shrinkage is augmented in some way. On the other hand, the drying shrinkage, this is a process that is inversely dependent on the massivity, because we say that drying shrinkage is mostly a superficial or surface related effect. So if we have a massive element, the drying shrinkage effects will only appear or mostly appear on the surface, but will not influence the volume of the element that much. We also need to remember that all of these processes not only occur in early ages, but also during the whole service life. And we can also experience some thermal effects during the service life, which are connected with seasonal or daily changes of temperature. But in this situation, again, since the effect from temperature is from the outside, then it decreases with massivity. So I told you that massivity is of great importance when we talk about reinforced concrete structures. And I said that usually we not really understand what massivity is. But as engineers, we want to have some more quantifiable measures for massivity. And here comes a very nice and widely used definition of massive concrete that comes from the ACI guideline on mass concrete, which says that mass concrete is any volume of concrete which dimensions are large enough that such a structure will require measures to be taken to cope with the generation of heat from hydration of cement and attendant volume changes to minimize cracking. So on one hand, we may say that this definition is very understandable because, as I said, we usually connect massivity with volume. But on the other hand, still, I believe, and a lot of people believe, that this measure is not very quantifiable. That's why we relate to other measures, and what comes at hand are geometrical criteria for massive structures. So again, this same guideline provides some measures for massivity, which relate the volume of concrete to the total area of exposed surfaces, which means that one component, the volume, will tell us how much heat will be produced, and the other component, the area of exposed surfaces, will tell us how quickly this heat can dissipate from the element, which will directly affect the internal temperature. This measure has been improved, let's say, by the scooter so this is an element of a European approach for more complex shapes, because of course, if we imagine a prism, then understanding this ACI definition is very straightforward, but for more complex structures, the scooter proposed another measure which also used some correction factor, which represents the shortest path for the heat to pass from core to the surface. And a similar measure was proposed by Flaga, so a Polish researcher, which is very similar to the massivity definition from ACI. The only difference is the inverse approach, even though if we go into detail into understanding of these two measures, we will see that the definition of the exposed surfaces in these two approaches is a little bit different. Also, what is important is that the proposal of Flaga is the only proposal which is actually quantifiable, because not only it allows to calculate the massivity, but then it also allows to classify structures according to the massivity. So it can allow the engineers to do some preliminary analysis to define if a structure is susceptible to thermal cracking or not. And these structures were satisfactory as long as concrete industry was based on Portland cement. Nevertheless, we know that for many years already, we tend to use mixed cements in our concrete, and therefore it is not enough to just base on geometrical criteria to define thermal cracking potential of the structure. That is why a working group within a RILEM Technical Committee in which I was involved proposed a corrected massivity, which uses their geometrical massivity, but proposed some correction factors to account for important other important factors that influence massivity. So as you can see, in this formula, we have three correction factors which are related to the following phenomena. First of all, this is a relative heat correction factor, which defines the type of cement that we use. So for Portland cement, the value of this correction factor would be 1, but for mixed cement, so the cements in which we use less caloric binders, this value would be lower than 1. Then another correction factor actually relates to the amount of cement, because using different types of cements, we also change the amount of cement from this typical one that used to be applied in typical concretes several years ago. And finally, we propose another correction factor, which takes into account technological conditions, so the initial temperature of concrete and ambient temperature. So this way, this corrected massivity can reflect the technological measures that can be taken into preventing thermal cracking. So eventually, how we interpret this corrected massivity, so we interpret it in such a way that if the value of this massivity factor is higher, it means that the structure is less prone to thermal cracking. And we have defined that if this massivity is below 2, then such a structure can be classified as massive, which means that it's susceptible to thermal cracking. And if it is above 2 and between 2 and more or less 15, then such a structure is medium thick, which means that thermal cracking potential is non-negligible. Only above the value of 15, we say that the structure is a thin-walled structure, and thermal cracking can be neglected, which means that we have conditions close to isothermal. And if you're interested more into this research, I refer you to a paper in which our team has presented this measure. So now when we defined, or we proposed a measure to say that a structure is susceptible to thermal cracking, now how do we reflect it in a structure? And this is how we move to the problem of restraint-induced cracking. So let me explain it on a simple example of a tie element, which is usually an element which we use to describe this type of phenomena. So if this element was not restrained, and if it was subjected to imposed deformation, so for example, thermal strain or shrinkage strain of a negative value, then such an element will just decrease in volume, and in such a linear element, we may, let's say, simplify it into the situation of a shortening, and this shortening will cause no stresses. The problem arises if such an element is restrained, because if the element is restrained and it is subjected to negative imposed deformation, so shrinkage, then an element tries to shrink, but it cannot because of the restraint, which means that a force will be produced in an element, and because this imposed deformation is negative, then we expect this force to be tensile. Then we can say that the value of expected stress within the element can be calculated from this simple formula. So this would be force over cross section, and if the value of this force reaches the so-called cracking force, which means that the stress reaches the tensile capacity of the element, then we expect a crack to occur in the element. And in the serviceability limit state of cracking design of the structures, we of course allow such a crack to happen, but we have to limit the width of this crack. And then the width of the crack, apart from the value of the strain, will depend also on the applied reinforcement, so its location, size, and the amount. And now how we correlate it to the actual structures. So I want to focus now on the actual externally restrained structures, and especially those types of elements that are of importance in my research, so the walls. We can find in the reality many examples of structures which have significant massivity, which means the massivity of a value which says that thermal cracking is non-negligible in such elements, so that the strains, imposed strains, will be formed in such an element during the service life, but which exhibit some form of an external restraint. And this encompasses such elements as breach abutments, tank walls, tunnel walls, or nuclear containment walls. in such elements, we observe the following cracking pattern. So this simple scheme shows you how cracks usually look in such elements. So we see that the cracks are vertical in the midspan of the element, and then they decrease in height and become a little bit slanted towards the ends of the element. So I don't want to dive deeper into this topic. If you are interested in more detailed characterization of cracking that we see in the walls, I refer you to another of the works of our team. But I would like to explain you what is the reason of such cracking in the walls. And for that, now I want to show you the results of numerical simulations of a wall. So you see here, we have a scheme of a wall, and we will be analyzing 1/4 of the wall. So in the next slide, you will see the interior of such a wall, and I will show you how the temperature and the corresponding stresses develop in such a wall. So in this simulation, on the left, you see thermal fields that develop in the wall. So as you can see, first we see the increase of the temperature due to the heat which is produced by hydration. But since this wall is exposed to external temperature, which is usually much lower than the adiabatic temperature that we expect in the wall, there is simultaneous cooling. And since the hydration heat is depleting as this process progresses, then the wall starts to cool down. And as a result, on the right side of this simulation, you see how stresses change. So in the beginning, we observe compressive stresses in the wall. And then as we pass the maximum hardening temperature, these compressive stresses diminish, they cross the zero value, and then tensile stresses start to develop. And in many of such elements, these tensile stresses reach significant values, which reach the tensile strength of the element. And as I explained at the beginning of this lecture, if the tensile strength is reached, it means that the crack is formed. So in the bottom of this slide in the simulation, you see the cracks that are forming. And as you have noticed, the pattern of these cracks correlates with the observed pattern in the real walls. So just to summarize, the situation looks like that. We can divide the behavior of such a wall into two phases. We have a heating phase, increase of temperature, which results in the increase in volume, especially increase in length, which means the wall tries to elongate. And in the cooling phase, when the temperature decreases, the wall starts to shorten, or it would like to shorten. But since it is restrained, this deformation is partially limited. That is why the stresses occur in the wall. So obviously, as I have shown, the maps of these stresses are pretty complex. So these stresses are variable within the volume of the wall. But what we can observe is that some simplifications can be made in a sense that when we look at the map of stresses along the length of the wall, they coincide with principal tensile stresses which are observed in the wall. So if we follow the trajectories of tensile stresses in the wall, we see that in the central part of the wall, the tensile stresses are practically horizontal, and the deviation starts to appear as we get closer to the end of the wall, which result from the wrapping effect of this end of the wall. And as a result, the cracks look like that. So they are vertical in the central part of the wall. So again, we are looking at a quarter of the wall, actually like a half length of the wall. So what we see here is that the crack in the center of the wall is vertical and reaches relatively the biggest height. And then the cracks become smaller and they turn to tilt towards the end of the wall. So how we also understand the principal tensile stresses is that the cracks will form in the direction perpendicular to these tensile stresses, and they will open in the direction which complies with the trajectory of the tensile stresses. So by this simple stress analysis, we have explained why we observe such shapes of cracks. And now how we apply it in the modeling. So we are coming back to this simple tie model. So again, here you see a wall with a typical cracking image. And as we have explained, the height of the cracks will depend on the effect of base restraint. And this is usually depicted with the use of the so-called degree of restraint. And I think it also can be explained rather naturally. So the biggest restraint, so the force, let's say, with which this wall is held, it is biggest at the joint, and then it decreases towards the free top of the wall. But anyway, as I have shown in the slide before, we may say that in the central part of this wall, the tensile stresses, so when we have this imposed deformation that is negative, which means it's trying to shrink the wall, and as a result, there is a tensile force that develops. So even though this tensile force is eccentric, we can say that in the central part, it produces pure tension. And since the design for cracking is focused on the maximum crack width, and the maximum crack width will appear in the center, we can simplify such a wall into a tie. So what we do is we cut a portion of the wall and we represent the portion of the wall as a tie, which means an element which is subject to axial tension. Nonetheless, this tie is not fully fixed, but it is only partially restrained. And the degree of this restraint that we use in this simplified model relates to the maximum degree of restraint because this is where we expect the maximum crack. So our design model would actually look like that. We will have a tie which is symmetrically reinforced with a reinforcement that we would design in such an element. But we don't assume full fixation. We only use a certain level of restraint. Therefore, when such a tie experiences shrinkage or a potential shrinkage, some part of this shrinkage will happen. So we say that some part of this strain is a free strain. So we will have some level of deformability. However, the rest of this imposed deformation is restrained, and this restrained part of strain will cause the actual stress, which can be calculated using such a simple formula. And why is that possible? Because for that purpose, we use the so-called simplified viscoelastic material model. And what are the basic assumptions of this model? So once again, let's come back to this diagram, which presents development of temperature in the element. I wanted to, just to remind you, we have a phase of rapid temperature increase when the hydration heat prevails, and then we have subsequent cooling when we deplete the hydration heat and the wall starts to cool to the ambient temperature. And this cooling phase is responsible for production of tensile stresses, as I showed in this more complex analysis. So in our simplified approach, we only consider this the thermal strain, which is caused by this temperature decrease. If we add to this the effect of shrinkage, like drying shrinkage and autogeneous shrinkage, this is how we obtain the total imposed deformation. And as I said, only the restrained part of this deformation is responsible for producing stress. So for the calculation of stress, we only take this R times E, which means the degree of restraint times total imposed deformation. And we use a linearization technique. So we can say that stress depends directly on strain, and the proportionality constant, according to the Hooke's law, is the modulus of elasticity, but we don't use the full modulus of elasticity. We use the so-called effective modulus of elasticity, which represents the effect of creep. So this modulus is much smaller than the actual modulus of elasticity. So as a result, we see that the actual stress will be smaller than in a typical linear analysis, but this is how it is. I mean, the effect of creep reduces the stress. And now let me show you briefly how design methods approach this. So what I will show in the next slides, you can read more about it in the papers that our technical committee produced in cooperation with engineers from ARUP. And I would like to present the methods that are used worldwide. I will try to be brief and not go too deep. But anyway, I will start with the European approach. So the approach that is proposed in Eurocodes, the standards, the family of standards that are commonly used in Europe, but also outside of Europe on other continents. So according to Eurocode 2, so this is a Eurocode dedicated to concrete structures, the width of the crack in general, not only the crack which is caused by imposed deformations, but the crack in general, can be calculated as a product of crack spacing and the difference in mean strengths between steel and concrete. Nonetheless, in case of restrained cracking, as I showed you, we don't have full restraint of the element, which means the value of or the width of the crack will depend not only on the applied reinforcement, but it will depend on the magnitude of restrained deformation. That is why the standard proposes to calculate the mean strain difference as being dependent on this restrained part of strain. So this way we take into account local effect of crack on the element. However, this value is reduced by the so-called extensibility of concrete, which means the ability of concrete to extend between cracks. So bluntly speaking, we say that cracks happen, but then concrete can regain some of its volume between cracks as a form of relief of stresses. So this is an important factor to account for. However, as far as the crack spacing is concerned, Eurocode proposes to use the same approach as it does for direct loading. And for that purpose, we use the so-called combined model, which is composed of two components. The one which results from bond slip theory, and which relates the slip length to the amount and location of reinforcement, and the other one which directly relates it to concrete cover. And in Europe, you can find a lot of variations of this approach, but all of them follow the same formula. So there are two main differences. First of them is whether the concrete cover is taken explicitly into account, because in most of the approaches, the concrete cover is taken into account in determination of the effective degree of reinforcement. And as you can easily see, the difference lies in the values of constants in this approach. So this is basically how we do it in Europe. However, there are other approaches used worldwide, which can be classified into groups depending on the location. So the second group I called Asian Pacific methodology, because these concepts are developed mostly in Australia and in Japan, and they are applied in various countries of Asian Pacific region. So first approach was proposed by Japanese organization, Japan Concrete Institute, and this approach is based on FEM-based calculations and statistical analysis. So in this approach, it is first required to determine the so-called cracking index. which relates tensile strength and tensile stress, but the standard explicitly recommends that this is determined using complex three-dimensional fan-based situations. However, the crack width is then calculated using a fully empirical formula, which uses the cracking index, which was determined this way. And this formula has been developed based on a database of results, which were calculated using fan-based situations. An alternative approach is used both in Japan and in Australia, and they are based on the similar approach, even though they were developed somehow independently. And what is important, because I don't want to go into too much deep detail, what is important in these approaches, in contrary to, for example, European approach, is that this approach doesn't assume that we have a stabilized cracking pattern. In contrary, when we know the value of the expected imposed deformation, we calculate the expected spacing of the cracks, and we compare it with the expected stabilized cracking. This way we know in which state we are, and we calculate the expected crack width accordingly, because it is important to remember that the slip length changes with the value of slip, which means the value of like the magnitude of the load, and these methods take this into consideration. Nevertheless, we can see in these equations some similarities in this European approach. So we can see that the stresses and the resultant crack width depend also on this restraint part of strain. So on the left, you see the original method, which was developed for a fully fixed tie. And to the right, you can see an adaptation which was prepared for a partially restrained element such as walls. So the difference here lies in the in the fact that we take into account the actual degree of restraint, and also that we account for the effect on creep, which is of great importance at the hardening stage when the value of creep is really high. And finally, we have an American approach, which was implemented in the previous version of the ACI report 207. Unfortunately, I saw that in the current one, it was removed. Nonetheless, I really wanted to investigate this approach. So here, the philosophy is a little bit similar to the European one. So to calculate the crack width, the same formula is used as for direct tension or direct bending. And the difference lies only in in some parameters, in some constants. In a sense that for tension, we expect greater widths of the cracks. That's why higher values of parameters are taken into account. The difference in the European approach and American approach is that in the European approach, first we calculate the crack spacing and then the resulting crack width. And in the American approach, it is the other way around. So first we calculate the crack width, and from that we can calculate the crack spacing. But if you remember, or if you look maybe at this lecture later, you watch it once again, you can make a direct comparison with this approach and the European approach, and you see that the formula is exactly the same. So the correlation between crack width and crack spacing is exactly the same as in the approach of Eurocode. The only difference is in this factor, which converts mean crack width to maximum crack width, because in the American approach this is 1.5 and in the European approach is 1.7. Another difference is that the American approach allows to check in which cracking stage we are with our loads, because we compare the crack spacing calculated this way with the crack spacing expected at stabilized crack stage. Another very interesting aspect of the approach proposed in the ACI report is the way how the required amount of reinforcement is calculated, which really allows for high optimization levels. Because I told you at the beginning of this lecture that the degree of restraint changes along the height of the wall. So normally in all of the previous approaches, we took into calculations the maximum value of degree of restraint. We calculated the expected crack width, and this allows us to calculate the required reinforcement. But if we do it this way, with such an approach, and we apply uniform reinforcement, it means that the higher we get in the wall, the more over calculation we achieve. In the American approach, it is explicitly stated that the wall should be actually divided into parts which are called lifts. And we can differentiate the amount of reinforcement needed at each height, because as you can see, we are producing not just one model, but multiple models of a partially restrained ties. And in each of these ties, we calculate the crack spacing, which depends on the degree of restraint which is present at this level of the wall. So this can really give us a lot of savings when calculating reinforcement. So in my research, I investigated all of those methods and I compared them. I was interested in seeing how they work, and I checked many different structures, and I tried to evaluate the predictive capacity of this method, and I observed a lot of discrepancies. So in this slide, I decided to show you just one theoretical example of a typical wall, which I wouldn't even call a massive wall. And you can see that the differences of calculations using different methods are really huge. So on the left, you can see the expected crack width, which is calculated using different methods. And on the right, you see the required amount of reinforcement that is needed to limit the crack width. So as I said, the differences are really huge. And with my team within RILEM, we have calculated many walls. And what we have observed is that even though these differences are really huge for typical walls, if we go for untypical walls, so the walls whose characteristics are deviating more and more from typical assumptions that we meet in the standards, these differences become even bigger. And in this last part of this lecture, I want to make some discussion, give some proposals of what we need to take into account to obtain results which are closer to reality. So how we should adapt, how we should wisely use these methods to obtain reasonable results. So first of all, I hope I was able to show you that since these structures are a little bit non-typical, it is important to remember that the width of the crack will depend on the actual level of the load. Because in such structures, we are never reaching the stabilized crack spacing, because only in the stabilized crack spacing the amount or the width of the crack will depend on the reinforcement. No, in this situation, the width of the crack will actually depend on the level of the load. So in order to predict the crack width properly, we need to be able to predict the value of this load, which means first of all, the magnitude of the imposed strain. And as I said at the beginning of the lecture, this imposed strain is composed of three components, one which is related to temperature, and the other two which are related to concrete shrinkage, the autogeneous shrinkage and drying shrinkage. So for these latter two, we have multiple methods that allow to predict it decently, I would say. Among them, I can enumerate different versions of Eurocode, but determination of thermal strain is much more complicated. So there are some proposals of how to calculate the thermal strain, so the temperature changes in a hardening structure. And we have some European approaches, but also ACI committee developed a really nice, really interesting method. However, I'm pretty confident to say that, especially regarding thermal strains, these methods are not really precise, and I support the approach of Japanese from the GACI, who say that currently, also given the abilities of fan-based methods, it is better to determine thermal and moisture fields using three-dimensional models and fan-based methods to calculate it. And I don't want to go deep into that because my time here is finishing, but if someone is interested, of course, we can have a chat on this, or I refer you to 2 papers that I have co-authored, which delve into proper modeling of thermal and moisture fields and resulting stresses in mass concrete structures. The second aspect, which is really important in determination of the load, is of course the degree of restraint, because it's not only important to assess the magnitude of imposed deformation, but also which part of this deformation will actually produce stress. And for that, we need to be able to determine the degree of restraint. And similarly, we have 2 roads. The first path is with analytical methods, and there are many methods that allow to assess the value of the degree of restraint, which come from many parts of the world. Some of them are standardized, some are non-standardized. But again, to be really precise, especially in complex structures, again, I support 3D modeling of the structures to get the actual value of the degree of restraint. And also I co-authored some research which goes deeper into this topic. And finally, when we talk about the degree of restraint, we need to remember one thing, that all of these methods that I presented here are related to the uncracked element. While actually, when we want to find what is the width of the crack, we are already in the cracked state. And there are some misconceptions regarding the degree of restraint in a cracked element. So I will not be discussing in detail this equation, but I just wanted to show it to you as a derivation of the model. So again, we come back to this basic model of a tie, which is partially restrained. And if we make subsequent derivations, we get to the formula of a degree of restraint in an element which is shown at the bottom of this slide. And we can easily see here that when we look at the stiffness of the element, we see that when the stiffness decreases, and this is what happens in cracking, then the restraint will actually increase. So one of the common misconceptions is that due to the cracking, the element becomes less stiff, which means it will have a smaller stress. Okay, on one hand, this is true, but also there is a counterbalancing effect of increasing restraint. So we may not be 100% fully confident that the resulting stresses in the cracking element will be lower. They might be still the same or even higher. Another aspect is when we have complex restraining conditions. So for example, when we have element which is not only restrained at the bottom, but also restrained at the ends. So the situation in an uncracked element looks like this. So we have a distribution of stresses, which looks like this. We have tensile stresses at the bottom of the wall and compressive stresses in the foundation. Once the crack is formed in the wall, what happens is that the stresses in an element increase. So this is what we would expect, which is on one hand really nice for the wall, but we should remember that the stresses will consequently also decrease in the foundation, which means we'll have less compression. If there is less compression in the foundation, it means the foundation will extend and it will pull the wall, consequently opening the crack. So again, lower stresses in the wall may not necessarily mean that the crack will be lower. And the final aspect, which is really important, is that the elements that we are discussing are thick elements. So elements of higher massivity, which means they will be thick. So again, using directly the time model might also cause a lot of misconceptions. Why is that so? So here I want to present a couple of slides that I have done following the research that was started by the University of Graz. So some research findings made by Professor Schlick and then with my company. So when we take into consideration a typical tie, so actually restraint element, we expect such a behavior. So as the tie is being tensiled with an increasing value of force, it will cause appearance or occurrence of subsequent cracks. And since this element is thin, these cracks will be through cracks and they will just appear one after another at the same level of force. The situation becomes complex when the element is thick and also the reinforcement is located very close to the surface, which means it doesn't really affect the core of the element. In such an element, you need, of course, much higher force to produce a crack because the area is higher. But at the same time, the behavior during cracking is different because since such a large amount of force is required to cause subsequent cracks, it is very hard to produce another through crack. On the contrary, we rarely observe another through crack, but the first crack is accompanied by a series of secondary cracks that only affect the effective tensile area, so the area where reinforcement is active. And we have investigated this using an original setup, which has been built by a team of Professor Schlick, which is called a restraining frame. And in this frame, we have tested a sample, which is extracted from a wall. And such a sample represents a slice of a wall at the height of one level of reinforcement. And it represents the actual thickness of the element. So the sample, if we look at it, looks like that. And here you can see a sample which represents a slice of a 1 meter thick wall. So the aim of this research is to investigate the development of cracks, and we have actually experienced this cracking pattern that I explained to you, but something else, some other interesting observation has been made during this research is that the effective, so the height of the effective tensile area was not complying with what is assumed in Eurocode and also many other standards around the world. So currently the state of the art says that the height of the effective tensile area in tensioned element equals more or less to 2.5 AS, where AS is the location from center of gravity of reinforcement to the free surface. What has been observed in this research is that actually this height depends on the thickness of the element. So as the element thickness increases, this height also increases. And that is why this effective height should be expressed as a function of relative location of reinforcement. And finally, similar research has been done in Germany at the Aachen University. I have also studied in detail this research in which some portions of massive elements were investigated, and it was investigated how the cracking process looks like in the elements of significant massivity, so that to show how they behave differently from typical thick elements to which we can apply a tie model. And the following has been observed in this research. First of all, this research confirmed this cracking pattern. So with increasing thickness, it is harder to produce another through crack, but the primary cracks are accompanied by secondary cracks, and these secondary cracks have very important meaning. In a sense that they are compensating the width of the crack. What it means? It means that if we look at the width of the crack I mean only the primary crack, then it is relatively small. But if we add together the width of all the cracks that form a kind of a set of cracks, so a primary crack and the secondary cracks, we can see that the total width of this system of cracks equals the width of the crack in the core. So what it means practically? It means that when we have a real structure, we usually check the width of the crack on the surface, because this is the only thing that we can actually do. And in such a situation, we would be relieved to see that the widths of the crack we see on the surface are very small. But what we are usually not aware of is that the width of the crack inside the element might be really big and reach even the magnitude of 1 millimeter, which is highly detrimental from the durability point of view. And the final observation that has been made over this research is that actually cracking is let's say statistical process, and that the cracking in an otherwise uniform element will happen in the weakest cross section. So I would call it the weakest link theory. It means that when we have a tie, which we would say is normally uniformly loaded, since concrete is not a homogeneous material, it's a highly heterogeneous material, we expect the crack to happen in the weakest section, which might result from many things, like location of aggregate or poor workmanship, which results in this heterogeneity. Anyway, where I'm heading is that in the design, we should not focus on mean tensile strength, but rather on the characteristics or lower bound concrete strength, because these calculations show that to predict the cracking force, so the force that causes crack, we should take this characteristic value, so the lower value, because the crack will always appear in the weakest part. And moreover, especially focusing on the massive concrete structures, we see an important size effect. So when we consider an element which is of 1 meter thickness, actually this value of the effective tensile strength, so the tensile strength that will produce, like the tensile strength reaching of which produce cracking, will decrease even further. So to summarize this lecture, what are the key takeaways regarding design of structures or massive concrete structures which are subjected to restrained cracking? So first of all, we must remember that models that we use for design are adaptations. So they are based on the models which we use for thin elements, which are subjected to direct loading. And the aspects which must be thoroughly considered in such model are as follows. First of all, we must take into account the actual cracking stage which we observe. So in contrary to the elements which are under direct loading, here we will never obtain stabilized cracking stage, which has a basic effect on the slip length, which is taken directly in calculations of crack width. Then, of course, we need to remember that in such elements, we don't have full restraint, we have only partial restraint. It means that cracking will have only local impact of internal forces. So as a result, the crack width will not only depend on the applied reinforcement, but on the magnitude of load. So we must be able to accurately calculate the value of this load. And also we must remember that this type of load, in contrary to service load, is a sustained load, which has an important effect on creep. That's why we should take into our calculations consideration into the effect of creep and how it reduces or how it influences the stresses. Then we must remember that to have all the above into account, there are some challenges in determination. First of all, the magnitude of imposed strains, especially thermal strains. and in restraint factor. That's why I opt in using of FEM-based modeling in determination of the following. And also the final very important aspect is that all the models that we currently use are calibrated models. So this means that the accuracy of using this model in calculation of the structures will be as good as these structures have characteristics similar to the database against which these models have been calibrated. And my extensive research has shown that if we go for untypical structures, and most of the externally restrained structures are untypical, the results deviate by far from what we would expect. So thank you again for being here. Thank you for your participation, and I'm open for questions. Sorry for being a little bit longer than the time I was allocated, but I hope you enjoyed the lecture. So thank you once again.
Thank you so much, Professor Jędrzejewska, for this incredible talk. I really appreciate. If you guys have questions, you can send to the Q&A box right there. I want to like really quickly share I just wanted to let you guys know that this talk is going to be available on your YouTube channels, and you can also like check some of our previous presentations that we hosted here in ACerS. So you can just go to the ACerS YouTube channel. And we also, I want to remind you guys to please send an abstract for our conference in the 50 Advanced in Cement-Based Materials that will be hosted in Colorado, Boulder. Yeah, thank you so much. Let me share again. Stop sharing. Yeah, okay, stop share. Okay. Yeah, and thank you so much, Agnieszka. That was very interesting to see all this like comparison. Also, it's very, for me, I right now I don't work so much in civil engineering, but in my civil engineering like topic, we often like normally that's where the civil engineers go for. They're gonna see like their local standards, and a lot of times we're missing all those details. And I would like to make a quick talk. So if like anyone here would be interested in collaborating with you, what topics right now do you think are really what are the future beholds, I think, your biggest challenges for the future, do you think?
Okay, so as far as the collaboration is concerned, I would really love to establish some real cooperation with someone who actively uses American standards, because unfortunately within my research network, I was not able to find anyone. So all our studies on the ACI approach are our interpretation. So I would be very curious to know how this really works in practice, if this approach is really used in practice, because as I said, I was extensively cooperating with Arup engineers. That's why I know how the Japanese, Australian, European methods work in practice. But on the ACI, this is just our interpretation. So this is one aspect that I would really like to investigate. But regarding the future, so as I said at the beginning, I go towards the use of, maybe using the word artificial intelligence is a little bit too much, but some machine learning techniques, or any tools that can automatize the design. So this is one aspect, and something that really is of great interest for me, but I know this is a very abstract concept, is using knowledge graphs. So I know that knowledge graphs become really an emerging technology of high impact in a very near future. And I would really like to develop towards this, because during all these years on working with this topic, I have gained really an extensive knowledge on this topic. And I mean, if you look at my papers, you would see that especially the recent ones are, I wouldn't maybe say a review papers because they are research papers, but in a sense that I want to combine knowledge from different teams, from different schools, from different philosophies. I really love that. And I think using knowledge graphs can be a nice tool to automatize it, because I reached a point that I know it can no longer be a human controlled. So I think we need some machine help with this to effectively use this huge amount of diverse knowledge.
Yes, yeah. With the current advances, how we can like, like how much, like those cloud computing can be very efficient and much faster. I
Yeah.
remember like people, I mean, in the past we're normally like coding in very, let's say, local like clusters of a computer, which was already pretty fast, but now you have like all those web service that you can like, I don't know, rent a machine for a few seconds that will like run all your things, so you can, do it very quickly. So
Yes, and
yeah,
you can actually do parametric studies, because so far, I mean, we had to choose wisely the parameters and try to see some trends, and it was not really efficient. And with the machines, it's another level, I believe.
Yes. Yeah, no, and so thank you so much. I think we don't have like much questions, but uh we've like the time and everything. Thank you so much everybody for attending this call. And I mean, it was very close presentation. I really enjoy it, and we're very honored to have you here. So thank you everyone. So see you. We're planning a few, oh sorry. We're planning a few more webinars to come, so stay connected. Yeah. Thank you.